Here in this problem, we're simplifying a rational expression and connecting it to its graph. So we have the expression x squared minus 9 divided by x squared minus 3x. And so the first step here is for us to factor the numerator and denominator completely. So as far as the numerator is concerned, that's the difference of squares. So it factors to x, then let me write that here, x minus 3 times x plus 3. And then for the denominator, x squared minus 3x factors to x times x minus 3. Okay, and so I can take a look here and look for common factors to cancel. We see here that we have the factor x minus 3 in both the numerator and in the denominator. So that means we can cancel it. So let's go ahead and do that. X minus 3 in the numerator and in the denominator. Okay, so now we have x equals 3 is still not allowed because it made the original denominator 0, right? But after canceling, we do have the simplified form of x plus 3 divided by x. And let me just write that over here so we can see that clearly. And so that is x plus 3 over x. Okay, and so that's the simplified form as I've stated. And as far as restrictions or excluded values are concerned, these come from the original denominator being 0. So you see here the original denominator x squared minus 3x. And we're going to set this equal to 0. So let me rewrite that as x squared minus 3x equals 0. Okay, so now we can go ahead and factor. We can factor out an x. And so that is x times x minus 3 equals 0. We can clearly see that x equals 0. So we'll say x equals 0, or x minus 3 equals 0. Okay, and so we solve for x by adding 3 to both sides, and we see here that x equals 3. Therefore, x cannot equal 0, x cannot equal 0, and x cannot equal 3. All right. So graphically, what do these mean? Well, I will say the factor we did not cancel, the x in the denominator, creates a vertical asymptote at x equals 0. So I'll just write that here. X equals 0 creates a vertical asymptote. So I'll just abbreviate that. And then the factor we did cancel, x minus 3, creates a hole or removable discontinuity at x equals 3. So I'll just write here x equals 3 creates a hole. Okay, so the next thing we can do here is find the exact coordinates of the hole. So in order to do that, we will plug in what we solved for x, which is 3, and we'll plug it into the simplified expression, x plus 3 divided by x. All right, so where you see this x, you're going to place a 3, and that'll give us the y value. So let's go ahead and do that. So 3 plus 3 over 3. And so that equals 6 divided by 3, which equals 2. Okay, so that means that we have a point at 3, 2, because remember, we have x equals 3, and then we have y equals 2. So let's write that. So that is 3, 2. And I'll just write that in red so that stands out. All right. And so now the next thing we can do here is just recognize that the whole is at the point 3, 2. And just also remember that there's an open circle there. The function is undefined at x equals 3, but the simplified version would pass through the point if it actually continued. And finally, as far as the horizontal asymptote is concerned, you compare the degrees of the numerator and denominator in the simplified form. So if you take a look here at the numerator and the denominator, well, both are degree 1, right? So that means the horizontal asymptote is the ratio of the leading coefficients, right? So the leading coefficients then is 1 over 1, which equals 1. So that tells us that the horizontal asymptote is at y equals 1. So let me just go ahead and write that here. So the horizontal asymptote, so y equals 1. There it is. Y equals 1, and that is the horizontal asymptote. Okay, so we have the vertical asymptote is at x equals 0. There is a hole at 3, 2. And then the graph will also tell us that the curve approaches y equals 1 on both sides. And so I've already graphed this inside of Desmos. And so I can show you what this actually looks like here. So let me just make this a little bit bigger so you can see it. And so you'll see the graph approaching the vertical asymptote at x equals 0, and then it levels off toward the horizontal asymptote at y equals 1. And a clear open circle is at 3, 2. Okay, so that's the full picture. The algebra does tell us exactly what features must appear in the graph, and so you can see those features right here. And so again, we have the vertical asymptote at x equals 0, and then we have the horizontal asymptote at y equals 1, and then you can just see that the graph is leveling off towards, and you skip over that hole, towards y equals 1 on both sides. All right, and so in the next problem, we're going to look at an exponential function.